The motivation is that the existing techniques rely on the fixed neuron selection criteria regardless of the DNN models or the coverage metrics. That is, these techniques do not change their selection criteria at all during the whole process of DNN testings. So for example, if we use deep explore techniques, we will always choose the inactivated neurons only. And likewise, if we use the third strategy of DL-Fudge, we will always choose neurons with the top weight only. And we observe that this unchanged strategy leads to suboptimal result when testing different DNN models with the different coverage metrics. For example, these two graphs shows the experiment result of the testing the same DNN model LINET5 to improve the different coverage metrics, neuron coverage and the top K neuron coverages. And as you can see, when trying to increase the neuron coverages, DL-Fudge is better than a naive strategy which randomly select the neurons. However, when trying to increase the top K neuron coverages, this naive random strategy is even better than the DL-Fudge. Likewise, these two graphs shows the result of the testing two different models, LINET5 and VGG19, with the same coverage metrics, TK and C. And the experiment results show that when testing LINET5 with the TK and C, random strategy was better than DL-Fudge. But when testing VGG19 with the same metric TK and C, DL-Fudge outperforms these naive random strategies. So in other words, the performance of the existing strategy is not constant and unstable across the diverse DNN models and the coverage metrics. So our goal is to design the stable strategy where its performance is consistent across the diverse DNN models and coverage metrics. So at a really high level, the key idea is to adaptively change neuron selection strategy optimized for a given DNN model and coverage metrics like chameleons. For example, if taking a LINET5 and neuron coverage as input, adapt is to adaptively change the strategy online to obtain the best result during the DNN testing. Likewise, if we're taking another model, VGG19, and another coverage metric, TKNC, adapt also tries to adaptively change the strategy online to obtain the best result during the testing. And to achieve this, adapt used the two key ideas. First, the parameterized neuron selection strategy and online learning. So before I talk more about each ideas, let me show the effectiveness of our technique adapt first. So in short, adapt consistently outperforms the existing strategy across the two coverage metrics and 4 different DNN models, such as LINET4, LINET5, VGG, and LESNET. And for example, when testing 2 LINET models, LINET4 and LINET5, adapt covered more about 10% activated neurons than the second best strategy, DL-Fudge. And adapt was also able to find diverse adversarial input exclusively across the various DNN models. So as you can see, the original label of the image on the top left was the number 1. But the generated input by adapt are classified as number 6 and the number 8 for RUNET 4 and RUNET 5 respectively. And for another example, the original label of the image on the left was grasshopper, but these two input mutated by the adapt on the right are classified as the chain link fence and long-horned beetles respectively. So if you look at the original image for chain link fence and the long-horned beetle below the images, these results are quite surprising to me. And for the next slide, let me explain in detail how this result can be achieved by adapt. So as I mentioned before, our technique is to adaptively change the neuron selection strategy during the testing process. That is, ours continuously change the selection criteria during the testings. So to do so, we use the two categories. First, we should define the space of possible neuron selection strategy that can be changed. And the second, we present an online learning algorithm that learns how to change the strategy effectively in this predefined space. First, to define the space of possible neuron strategy, we parameterize the strategy that can be changed, which corresponds to the parameterized search heuristic like ICSI 2018. And this work, in this work, a single neuron selection strategy corresponds to a real number of vectors. And using this parameterized strategy, we score each neuron and select the k neuron with the highest scores. So suppose that this number in this figure represent the score of each neurons, and then we will select these two neurons with the highest score highlighted in blue. And to score each neurons, we represent each neuron as feature vectors. And a feature in this work is a Boolean predicate on neurons. And we manually designed 29 atomic features, but we tried to design the feature with the simplicity and generality. And we can classify 29 features into the constant and the variable features, where the key difference is whether the Boolean value of the feature changes during the neural network testing or not. And more specifically, the value of constant feature for the same neuron does not change, and while the value of variable feature may change. For example, constant feature number 9 checks whether the neuron is in the activate layer or not. And the Boolean value for each neuron never changes while testing is over. So this is the constant feature. So after representing each neurons in the DNN model to a Boolean feature vectors, and we used our parametric strategy, which is a linear number vectors. That is, we can score the neuron by simply calculating linear combination of feature vector and the selection strategies. Finally, we choose the two neurons N1 and N3 with the highest scores. Okay, the second key idea is to learn how to change the neuron selection strategy effectively in the predefined space for maximizing a given coverage matrix. So our domain-specific learning algorithm consists of two phases which are testing pace and the learning pace. And more specifically, the learning pace has two stages, extract stage and combine stage. So let's look at the first pace testings. So in the testing phase, a given neural network model will be tested using the M neuron selection strategy generated in learning phase, except for the first iterations. This is because there is no learning data at the first iteration, so we just randomly generated neuron selection strategy at the first iterations. And in our work, as I mentioned before, a single selection strategy corresponds to 29-dimensional real number vectors. So after testing DNN models with these 4 neuron selection strategy in this example, and this technique returns the set of covered neurons for each strategies. For example, the strategy S1 succeeded in covering the neurons N1 and N2 and N5. And after returning the set of covered neurons for each strategy, we move on the next stage, extract. In the extract strategy stage, we first collect the at most k good neuron selection strategy that collectively achieve the highest coverages. For example, in this example, when selecting only 2 strategy S2 and S5 among the 4 strategy, we can achieve full coverage from the neuron N1 to N5. So we select these 2 strategies, S2 and S4. And additionally, we just select the strategy that totally achieve the high coverages. In this case, we add the second neuron selection strategy again, as it achieves the highest coverage among the 4 strategies. And at the next stage, we generate the new neuron selection strategies by combining the extracted neuron selection strategy like genetic algorithms. So to do so, we first randomly choose the 2 strategy among the extracted ones. Suppose that S2 and S4 are selected randomly. And then, as you can see, we simply mix the feature weights of the S2 and S4 like the new strategy S5. Finally, we add a small noise to the mixed strategy S5 and normalize that strategy. So in this way, using the following 4 steps, we generate M neuron selection strategy, and then we move on to the testing phase with this new strategy from the S5 to S8 again. In this way, by repeating the 2 critical phases is extract and combine stages, our learning algorithm will get smarter thereby achieving high coverage and finding many adversarial inputs. For evaluation in adapted papers, we use the 2 well-known coverage metrics, neuron coverage and the top K neuron coverages. And we also use the 2 representative data set, MNIST and ImageNet. And we also use the 2 neural network models for each coverage metrics, LUNET4, LUNET5, and VGG and ResNet. And we compared our technique adapt with the 5 existing techniques, including a naive random neuron selection strategy and deep explore and 2 versions of the DL fudge, which is the DL fudge best and DL fudge round robin. And the tensor fudge, which is a representative of the gray box testing method. As shown at the beginning of this lecture, ADAPT significantly outperformed the existing strategy and consistently achieved the high coverage across the dataset and the neural network models. For example, during the same testing budget, which is one hour, our technique is able to cover more about 3,000 neurons than the second best strategy, the other one. In terms of the number of the found adversary input, our technique ADAPT also outperformed all the existing strategy. For example, when testing LINET-5, our technique ADAPT found about 4,000 adversary input, while the best strategy maybe managed to found about 200 adversary input. And ADAPT also shows its strengths in terms of the number of found labels and the found city. And for your interest, our tool ADAPT is also publicly available tool for testing diverse deep neural network models. And our tool also offers easy to follow tutorials. So if you are interested, you just download and use it. Okay, let's sum up these lectures. First, smart neuron selection is one of the key components of the white box testing. Second, many neuron selection strategies have been presented to address the challenge of white box testing for testing real-world DNN models. In particular, we learned the state-of-the-art technique ADAPT that learns and changes neuron selection strategy online during the testing procedures. Lastly, despite the great progress of DNN testing, these white box testing methods are still at early stages, so we have a lot of chance to improve the effectiveness of white box testing of DNNs. Okay, this is the end of this lecture, so see you soon, everyone.